Look around you. Take a moment, genuinely, to register what surrounds you right now. The surface you're resting on, the air moving through your chest, the light traveling from a screen into the extraordinary biological machinery of your eyes, converting photons into meaning. All of this, every single element of it, should not exist. Not as a matter of opinion, not as a philosophical provocation designed to sound profound. As a matter of cold, verified, peer-reviewed physics, the universe that produced you was under no obligation to produce anything at all. And the more precisely we measure the conditions that made your existence possible, the more the numbers begin to look less like science and more like something that has no right to be true. If this kind of question unsettles you, the good kind of unsettled, the kind that makes the world feel larger and stranger than it did 5 minutes ago, consider subscribing. And if what you're about to hear is the sort of thing you'd want someone else to sit with, leave a like. It genuinely helps this reach the people who are ready for it. We need to start at the beginning, not the beginning of Earth, not the beginning of life, the beginning of everything, the moment before which the word before may not have had any meaning at all. Approximately 13.8 billion years ago, according to measurements derived from the cosmic microwave background radiation, a faint thermal echo, first detected by Arno Penzias and Robert Wilson in 1965. The universe emerged from a state of almost incomprehensible density and temperature. The Big Bang, a term that, almost universally, is misunderstood. It was not an explosion in the sense that word normally implies. There was no pre-existing space for the explosion to expand into. Space itself was created in that instant. Time itself was created in that instant. Whatever existed before, if before is even a coherent concept when time has not yet begun, is a question that sits at the very edge of what modern physics can address. Stephen Hawking, in A Brief History of Time, suggested that asking what came before the Big Bang is like asking what lies south of the South Pole. The question assumes a geometry that doesn't apply. The boundary simply does not extend in that direction. What we do know is what happened in the first moments after, and those moments were not quiet. In the first fractions of a second, the universe was a plasma of unimaginable energy, temperatures in the trillions of degrees, densities so extreme that our entire observable cosmos was compressed into a region smaller than a proton. In those conditions, the fundamental forces of physics, gravity, electromagnetism, the strong nuclear force, the weak nuclear force, were behaving in ways that have no parallel anywhere in the universe today. Physicists believe, though they cannot yet confirm, that in those earliest moments, these forces may have been unified into a single superforce. What caused them to separate, to crystallize into the distinct forces that govern chemistry, light, and the structure of matter, is one of the deepest unsolved problems in theoretical physics. But here is the thing. As those forces separated, as the universe cooled from its initial state into something slightly less catastrophic, a series of values were established, constants, numbers that are baked into the fabric of reality itself, the strength of gravity, the charge of the electron, the ratio of the mass of a proton to the mass of an electron, the cosmological constant, which describes the energy density of empty space and governs the rate at which the universe expands. These are not values that physics currently explains from first principles. They are simply measured, observed, recorded, and when you look at what would happen if any one of them were even fractionally different, The results are immediate and total. Change the strength of the strong nuclear force by 2%. Stars can no longer fuse hydrogen into helium. No stellar energy, no heat, no light. The universe remains a dark, slowly cooling expanse of gas forever. Increase the cosmological constant by a factor of just a few. The universe expands so rapidly in its earliest moments that matter never has time to clump together under gravity. No galaxies form, no stars, no planets. A universe of thinning soup, accelerating endlessly toward a cold, structureless equilibrium. Alter the fine structure constant, the dimensionless number that governs the strength of electromagnetic interactions, and the chemistry of carbon becomes impossible. Carbon, the atom on which all known life is architecturally dependent, relies on a specific quantum mechanical coincidence, first identified by the astrophysicist Fred Hoyle in 1953. Hoyle was trying to explain how carbon could be produced in stellar interiors, and he realized that the nuclear energy levels of carbon and oxygen had to sit in a precise relationship to each other, a relationship so specific that Hoyle, who was famously not a religious man, concluded that the universe appeared to have been put up job. His words, a calculated arrangement. He never resolved his discomfort with that conclusion, and neither has physics in the 70 years since. The physicist Paul Davies, in his 1982 book, The Accidental Universe, attempted to compile the full list of these coincidences, the constants that appear not merely fine-tuned, but hyperbolically fine-tuned for the emergence of complexity. The cosmological constant alone sits within a tolerance of 1 part in 10 to the power of 120. That is not a number with any real-world intuition attached to it. For reference, the total number of atoms in the observable universe is estimated at roughly 10 to the power of 80. The precision required in the cosmological constant is 13 orders of magnitude tighter than the number of atoms in everything you could ever observe, in every direction, with the most powerful telescope ever built. The physicist Roger Penrose, in The Road to Reality, attempted to put a single number on the probability of a universe like ours arising by chance from the space of all possible initial configurations. His estimate, 1 in 10 to the power of 10 to the power of 123. This is not a number that can be meaningfully compared to anything. It is not small. It is not even in the category of things to which the word small applies. It is a notation for something that, in any ordinary statistical sense, should be considered impossible. And yet, here we are. This is where the story becomes genuinely strange, because the scientific response to this observation has not been to accept that the universe is simply, inexplicably, extraordinarily fortunate. That would be intellectually unsatisfying in a way that physicists find intolerable. Instead, the 20th century produced 2 broad categories of explanation, and neither of them is comfortable. The first is the anthropic principle, formulated most rigorously by the physicist Brandon Carter in a 1973 paper presented at a symposium in Krakow, Poland, marking the 500th anniversary of Copernicus's birth. Carter's argument was, at its core, simple. We should not be surprised to observe a universe compatible with our existence, because a universe incompatible with our existence would not be observed. We are, by definition, only capable of asking this question from inside a universe that produced us. The fine-tuning is not a mystery if you accept that observers can only exist in the subset of possible universes that permit observers. This reasoning sounds almost circular, and in some formulations it is. Its critics, including the philosopher John Leslie and the physicist Lee Smolin, have argued that it sidesteps the question entirely. The fact that we can only observe a life-permitting universe doesn't explain why TGID, life-permitting universe, exists at all. The anthropic principle, in its weak form, is less an explanation than a constraint on our epistemic position. It tells us where we must be standing. It says nothing about how this particular place came to exist. The second category of explanation is more radical and considerably more unsettling. It is the multiverse, a concept that arises independently from several branches of theoretical physics, including inflationary cosmology and string theory, and which we will examine in full detail later in this series. The short version is this: if our universe is one of an effectively infinite number of universes, each with its own randomly distributed physical constants, then the fine-tuning problem dissolves. Of course, some universes will be compatible with complexity. In an infinite ensemble, all configurations are realized. We are simply the ones who got lucky, or rather, the ones for whom luck, in this context, becomes a tautology. But notice what this explanation costs. It resolves the fine-tuning problem by making our universe not special, but utterly ordinary, one of an uncountable distribution of configurations, almost all of which are cold, dark, and structureless. It relocates the improbability from our universe to the machinery that generates universes, and that machinery is entirely beyond our capacity to observe or test. We are, at present, unable to confirm or falsify the multiverse. It lives in the theoretical foundations of our best physics, but it is not, in the strict Popperian sense, science. Not yet, anyway. Here is what we can say with confidence. The universe that exists, the one measurable, observable, instrumentally verified cosmos that stretches for 46 billion light-years in every direction from where you are sitting right now, is configured in a way that permits chemistry, stellar evolution, planetary formation, and biological complexity. Every measurement we have taken confirms this. Every experiment refines the precision of the constants, and in doing so, makes the fine-tuning more acute rather than less. The physicist Freeman Dyson, in his 1979 memoir Disturbing the Universe, wrote something that has stayed in the minds of cosmologists for decades. As we look out into the universe and identify the many accidents of physics and astronomy that have worked together to our benefit, it almost seems as if the universe must in some sense have known we were coming. Dyson was not a religious man. He was not making a theological argument. He was describing a discomfort, a precise, quantifiable, scientifically grounded discomfort, with the coincidence of our existence. The discomfort has not faded. It has, if anything, deepened. And we have not yet begun to talk about the real problem, because the fine-tuning of the constants, extraordinary as it is, merely establishes the possibility of complexity. It tells you that stars can burn, that chemistry can occur, that planets can form. It does not tell you how a universe of hydrogen and helium becomes a universe of living cells. That transition, from the laws that permit chemistry to the chemistry that produces biology, involves a second, entirely distinct layer of improbability, one that is, in many ways, even harder to account for. To understand it, we need to follow the universe through its next several billion years. We need to watch what happens when a cosmos full of the simplest atoms, hydrogen with its single proton and helium with two, is placed under the slow, patient, inexorable influence of gravity. We need to understand what stars actually are, what they actually do, and why the ones that existed before our sun are the reason your blood is red. We need to understand that before a single cell could divide on Earth, the universe had to build a forge, and then that forge had to explode. The cosmos, it turns out, does not produce life quietly. It produces the ingredients for life through some of the most violent events in the history of space-time, and then scatters them across distances so vast that the atoms which eventually assembled into you spent billions of years drifting alone through interstellar space, waiting for gravity to bring them home. The accident that produced you was not a single event. It was a sequence of catastrophes, each one dependent on the last, stretching back to the first second of the universe. And the deeper you follow that chain, the less it looks like accident, and the more it looks like something for which we have not yet found the right word. There is a particular kind of vertigo that comes not from height, but from time, from trying, genuinely trying, to hold in your mind a number so large that every analogy available to human language collapses before it reaches the scale. We experience this when we look at geological time, at the 4.5 billion years of Earth's history compressed into a single calendar year, where all of human civilization occupies the last 14 seconds of New Year's Eve. We experience it when we look at cosmological time, at a universe 13.8 billion years old, in which our entire solar system is a relative newcomer. But neither of those exercises prepares you for the other direction, for the compression, for what happens when you take the first second of the universe, a single second, and begin to unfold what occurred inside it. Because everything that followed, every star, every element, every ocean, every mind, was decided in that second, not metaphorically, literally. The negotiations that took place in the first moments of the universe were so consequential, so structurally deterministic of everything that came after, that cosmologists sometimes speak of them with a kind of hushed precision, the way a surgeon might speak of the first incision. Everything downstream depended on what happened here, and what happened here was, by any rational account, not supposed to go the way it did. Let us start with temperature. In the very first moments after the Big Bang, within the first 10 to the power of negative 43 seconds, a unit called Planck time, which represents the smallest interval of time that current physics can meaningfully describe, the universe existed at a temperature of approximately 10 to the power of 32 degrees Celsius. This is not a temperature that has any analogy in lived experience. The surface of the sun sits at roughly 5,500 degrees. The core of the sun reaches 15 million. The most powerful particle accelerator ever built, the Large Hadron Collider at CERN, produces temperatures in collisions of around 10 trillion degrees, and that remains 14 orders of magnitude below the temperature of the universe in its first instant. We are not dealing with heat in any ordinary sense. We are dealing with a state of energy so extreme that the concept of matter, of particles with defined properties, did not yet exist. What existed instead was a quark-gluon plasma, a soup of the most fundamental constituents of matter, moving at velocities approaching the speed of light, colliding and annihilating and reconstituting billions of times per second. The universe, in those first moments, was not a place. It was a process, a continuous, furious renegotiation of energy into matter and matter back into energy, happening everywhere simultaneously, with no structure, no differentiation, no direction. And then the universe began to cool. As temperature dropped, something extraordinary happened. quarks began to bind together under the influence of the strong nuclear force, forming the first protons and neutrons. This occurred approximately 1/10,000th of a second after the Big Bang, still within that first second, still at temperatures of trillions of degrees, and it represented the first moment in the history of the cosmos that anything resembling stable matter existed. Protons and neutrons, the building blocks of every atomic nucleus that has ever formed, the substrate of the periodic table, the foundation of chemistry, but their formation immediately created a crisis. For every particle of matter that condensed from the energy of the early universe, an equal and opposite particle of antimatter was produced alongside it. This is not an assumption or a theoretical extrapolation. It is a measured, confirmed consequence of the symmetry laws that govern particle physics, specifically a principle called CPT symmetry, which describes how physical laws behave under simultaneous reversals of charge, parity, and time. In a perfectly symmetric universe, matter and antimatter should have been produced in precisely equal quantities, and had they been, what followed would have been instantaneous and total. Every particle of matter would have encountered a corresponding particle of antimatter. They would have annihilated each other. The energy released would have dispersed as photons, pure light, and the universe would have been left with nothing. Radiation expanding forever through empty space. No atoms, no chemistry, no time worth inhabiting. That is the universe that the mathematics predicted. That is not the universe we live in. In 1967, the Soviet physicist Andrei Sakharov, the same man who had played a central role in developing the Soviet hydrogen bomb and who would later become one of the USSR's most prominent dissidents and human rights advocates, published a paper in the journal GTP Letters that quietly identified the conditions necessary for the universe to produce more matter than antimatter. His three conditions, now known collectively as the Sakharov conditions, described the specific circumstances under which the symmetry between matter and antimatter could be broken. The paper was 3 pages long. It was largely ignored for nearly a decade. When physicists eventually returned to it, they found that it described something that the early universe must have undergone, a process called baryogenesis, in which the fundamental symmetry between matter and antimatter was violated at a level almost too small to measure. For every billion antiparticles produced, the universe generated approximately 1,000,000,001 particles of ordinary matter, a surplus of 1 in a billion, a rounding error in the ledger of creation. When matter and antimatter annihilated each other across the entire observable universe, that surplus survived. And that surplus, those 1 in a billion leftover particles, is everything. Every proton in every atom in every star, in every galaxy, the chair beneath you, the oxygen in your blood, the neurons generating the thought you are having right now. All of it is the residue of an asymmetry so small that physicists spent decades struggling to find its source. We still do not fully understand it. The standard model of particle physics, the most precisely tested theoretical framework in the history of science, predicts CP violation, the asymmetry between matter and antimatter, but predicts it at a level far too small to account for the surplus we observe. Something produced more asymmetry than our best theory anticipates. Whatever that something was, it happened in the first fractions of a second, and it has never happened since. We are, in the most literal sense, living inside a mystery that the universe has not finished explaining. By the time the universe was 1 second old, its temperature had dropped to approximately 10 billion degrees. Still extraordinary, but now within a range where another critical process could begin. Protons and neutrons, now stable, began interacting through the weak nuclear force in a process called neutrino decoupling. The universe was becoming, very slightly, more structured, more differentiated. Particles were beginning to settle into roles. And then, between approximately 1 second and 3 minutes after the Big Bang, something happened that would directly determine the chemical composition of everything that followed. The temperature dropped to around 1 billion degrees, the threshold at which protons and neutrons could fuse together without immediately being torn apart by the ambient thermal energy. For those few minutes, the entire universe was a nuclear reactor. This process is called Big Bang nucleosynthesis, and its theoretical framework was established in 1948 by the physicist Ralph Alpher and his supervisor, George Gamow, in a paper that Gamow, with characteristic irreverence, added the name of physicist Hans Bethe to purely for the pleasure of having it authored by Alpher, Bethe, and Gamow, the Alpha Beta Gamma paper, as it became known. In it, they predicted that the early universe should have produced hydrogen and helium in a ratio of roughly 3:1 by mass, with trace amounts of lithium and beryllium. When astronomers later measured the elemental abundances of the oldest, most chemically pristine stars in the universe, stars formed from material that had never been processed through a later generation of stellar nucleosynthesis, they found exactly that ratio. The prediction was confirmed to a precision that remains one of the great triumphs of physical cosmology. But notice what Big Bang nucleosynthesis did not produce: carbon, nitrogen, oxygen, phosphorus, sulfur, iron, calcium, every element heavier than lithium on the periodic table, every element on which biological chemistry depends, emerged from the Big Bang as essentially zero. The universe, at 3 minutes old, was chemically almost entirely inert. 2 elements, 3, in trace amounts, a cosmos of staggering energy and mathematical elegance, containing almost nothing from which complexity could be built. 3 minutes after the Big Bang, nucleosynthesis ended. The universe had expanded and cooled to the point where fusion could no longer occur. The window had closed, and for the next approximately 380,000 years, nothing of structural significance happened. The universe was opaque, a plasma of charged particles through which light could not travel. Protons and electrons existed separately, unable to combine, because the ambient temperature was still too high for electrons to remain bound to nuclei. The universe glowed, but it could not be seen through. It was a fog of light and heat, slowly thinning. Then, at 380,000 years, the temperature dropped below approximately 3,000 degrees, the threshold at which electrons could finally bind to protons. Hydrogen atoms formed. For the first time, the universe became transparent. Light, freed from the plasma, streamed outward in all directions. That light, stretched by 13.8 billion years of cosmic expansion into microwave radiation, is what Penzias and Wilson detected in 1965. What they heard as static in their antenna was the oldest light in the universe. The afterglow of the moment matter and energy first separated. These moment the cosmos first became legible. This is the cosmic microwave background radiation, and it is among the most information-rich signals we have ever detected. Its tiny temperature fluctuations, variations of 1 part in 100,000, map the density variations in the early universe that gravity would eventually amplify into the large-scale structure of the cosmos. The seeds of every galaxy cluster, every filament, every void in the cosmic web were already encoded in that radiation imprinted in the first fractions of a second by quantum fluctuations that the process of inflation stretched to cosmological scales. The largest structures in the observable universe are, in a very real sense, quantum effects made enormous. After recombination, as this transition is called, the universe entered a period cosmologists refer to as the cosmic dark ages. There were no stars yet, no sources of light, just hydrogen and helium, distributed with extraordinary uniformity, drifting in darkness. The universe was patient in a way that has no human analogy. For hundreds of millions of years, nothing happened that you could observe, nothing that would register on any instrument. Just the slow, silent thickening of slightly overdense regions as gravity pulled matter toward itself across distances of millions of light years. And then, somewhere between 100 and 500 million years after the Big Bang, the precise timing remains an active area of research, with observations from the James Webb Space Telescope currently pushing the confirmed detection of early galaxies to within 300 million years of the Big Bang. The first stars ignited. The Dark Ages ended. The universe lit up. Those first stars were nothing like our Sun, formed from pure hydrogen and helium, containing none of the heavier elements that act as opacity sources in later stellar generations. They were able to accumulate mass at extraordinary rates. Theoretical models suggest they may have reached hundreds of times the mass of the Sun, behemoths that burned through their fuel in millions of years rather than billions. Their lives were brief and violent. Their deaths were cataclysmic, and their deaths were the most important thing that had happened in the universe since the first second. Because inside those stellar cores, at temperatures of hundreds of millions of degrees, nuclear fusion was building what the Big Bang could not: carbon, oxygen, neon, silicon, iron, the heavy elements, the chemistry of complexity, the raw materials for everything biological that would ever exist, the 1 in a billion asymmetry that saved matter from annihilation, the 3-minute window that established the hydrogen-helium ratio, the 380,000-year wait for the universe to become transparent, the hundreds of millions of years of darkness before the first star ignited. Each of these was a gate. Each one had to open at precisely the right moment, at precisely the right value, for the sequence to continue. This is not a narrative we are imposing on the universe after the fact. These are measured events, confirmed by instruments, constrained by theory, reproducible in mathematical models. The universe ran a gauntlet of improbabilities in its first second, and then continued running it for hundreds of millions of years, before it produced a single atom of carbon. And carbon, it turns out, was only the beginning of the problem. Because atoms are not life, elements are not biology. A cloud of carbon and oxygen and hydrogen scattered across interstellar space is still, in every meaningful sense, dead. Between the scattered wreckage of exploded stars and the first molecule capable of copying itself, there lies a distance that physics has spent decades trying to measure, and biology has spent decades trying to cross. What happened in that distance is the subject of one of the most heated, most consequential, and most genuinely unsolved debates in the history of science. A debate that forces us to ask not just how life began, but whether, given everything we now understand about the conditions required, it should have begun at all. There is a sentence that sounds, on first encounter, like poetry, like the kind of overwrought cosmic metaphor that gets printed on motivational posters alongside photographs of nebulae. You have almost certainly heard it. You are made of stardust, and because you have heard it so many times, in so many contexts, stripped of its weight and its precision and its genuine scientific content, it has probably stopped meaning anything to you. It has become decoration, background noise, one of those phrases that gestures at profundity without requiring you to actually confront it. So let us confront it properly. You are not metaphorically made of stardust. You are not spiritually descended from the stars in some vague, poetic sense. The calcium mineralized into your bones was forged in the nuclear furnace of a star that exhausted its fuel and exploded billions of years before the Earth existed. The iron that gives your blood its color, that sits inside every hemoglobin molecule, ferrying oxygen through your body right now, was synthesized in the collapsing core of a massive star in the final seconds of its life and scattered across interstellar space by an explosion of such violence that, for a brief period, that single star outshone the entire galaxy it lived in. The oxygen filling your lungs with each breath, the carbon forming the backbone of every biological molecule in your body, the nitrogen bonded into every amino acid and nucleotide you possess, all of it was built inside stars. All of it was dispersed by their deaths. All of it drifted through the cold and dark of interstellar space for millions, sometimes billions, of years before gravity gathered it into the molecular cloud that would eventually collapse into our solar system. You are the universe recycling itself, and the recycling process required an almost incomprehensible amount of destruction. To understand why, we need to go back to the state the universe was in at the end of Chapter 2. The cosmic dark ages had ended. The first stars had ignited. But those first stars, the population 3 stars, as astronomers classify them, a designation for objects so ancient that not a single confirmed example has yet been directly observed, were not stars in the sense that our sun is a star. They were something stranger, something more violent, and something far more consequential. Because they formed from gas that contained only hydrogen and helium, the only elements the Big Bang produced in meaningful quantities, they had none of the heavier elements that act as opacity sources in stellar interiors. In a star like our sun, the presence of metals, a term astronomers use, somewhat confusingly, to describe any element heavier than helium, helps regulate the rate at which the stellar core radiates energy. Metals absorb photons, scatter them, slow their journey from the core to the surface, and in doing so, create an outward pressure that limits how quickly the star can accrete mass during formation. Population 3 stars had none of this regulation. Their formation was, in a sense, uncontrolled. Theoretical models developed over the past 2 decades, including work by Volker Braun at the University of Texas and the late Richard Larson at Yale, suggest these first stars routinely reached masses of 100 to several hundred times that of the Sun. Some models allow for objects approaching 1,000 solar masses, a scale for which the word star feels almost inadequate. At those masses, everything happens faster. The core temperatures needed for nuclear fusion are reached almost immediately. The rate at which hydrogen is consumed is not linear, but exponential relative to mass. A star 10 times the mass of the Sun burns roughly 10,000 times more brightly and lives approximately 100 times less long. Extrapolate that scaling to a star of 100 or 300 solar masses, and you arrive at a lifespan measured not in billions of years, not in millions, but in a few 100,000. On cosmological timescales, this is an eye blink. On any human timescale, it is still an eternity. But the point is this: the universe's first generation of stars was born, lived, and died before the cosmos was even 1 billion years old, before our Milky Way had fully assembled, before the solar system existed by more than 9 billion years. And when they died, they changed everything. The story of how stars build heavy elements begins with a problem that troubled physicists for most of the first half of the 20th century. By the 1940s, it was understood that stars generate energy through nuclear fusion, the process by which lighter atomic nuclei are forced together under extreme temperature and pressure to form heavier ones, releasing energy in the process. Hydrogen fuses into helium. That much was clear, established through the work of Hans Bethe, who published the first complete theoretical account of stellar energy generation in 1939 and received the Nobel Prize for it nearly 30 years later. But helium, when it fuses, creates a problem. Two helium nuclei, each containing 2 protons and 2 neutrons, fuse to form beryllium-8, and beryllium-8 is catastrophically unstable. It decays back into 2 helium nuclei in less than 1/10,000th of a billionth of a second. This is a barrier, a wall. If stellar nucleosynthesis cannot get past helium, then carbon, the foundation of all known biochemistry, can never be produced in any significant quantity. And if carbon cannot be produced, the periodic table effectively stops at helium for practical purposes. The universe remains chemically simple. Life, as we know it, becomes impossible. This is where Fred Hoyle enters the story, and where the history of astrophysics takes one of its most remarkable turns. Hoyle was, by any measure, one of the most consequential and most infuriating figures in 20th century science. He was the man who coined the term Big Bang, sarcastically, in a 1949 BBC radio broadcast, as a way of mocking what he considered an implausible theory. He was wrong about the Big Bang. He spent much of his later career defending positions on the interstellar origin of life, on alternative cosmological models, that the scientific mainstream rejected with varying degrees of patience. But in 1953, working at Caltech, he made a prediction so precise, so counterintuitive, and so correct that it has been cited ever since as one of the most striking examples of theoretical reasoning in the history of physics. Hoyle realized that the only way carbon could be produced in stellar interiors in the quantities we observe, the quantities required for life, was if there existed a specific resonance state in the carbon-12 nucleus at a very particular energy level. This resonance would allow a 3-body reaction to occur. 2 helium nuclei first form beryllium-8, and then, before it can decay, a 3rd helium nucleus collides with it, producing carbon-12 in an excited state that then releases a gamma ray and stabilizes. The triple alpha process, as it is known. For this to work, the energy of the carbon-12 resonance state had to sit at almost exactly 7.65 million electron volts. Hoyle, working backward from the existence of carbon in the universe, predicted this value before it had been measured. He then walked across campus to the nuclear physics laboratory of William Fowler and asked them to look for it. They found it at 656 million electron volts, within a fraction of a percent of Hoyle's prediction. Fowler received the Nobel Prize in Physics in 1983 for his work on nuclear reactions in stars. Hoyle, controversially, did not, an omission that remains one of the most debated decisions in the history of the Nobel Committee. But what both men had established, together with the pioneering work of Margaret Burbage, Geoffrey Burbage, and Fowler in their landmark 1957 paper known as B2FH, was a complete theoretical account of how stars build the heavy elements. The paper is titled Synthesis of the Elements in Stars, and it is, without exaggeration, one of the most important scientific documents of the 20th century. What B2FH described was a hierarchy of burning stages inside a massive star, a layered, onion-like structure in which different nuclear fusion reactions proceed at different temperatures and depths. Hydrogen burns in the outermost layers. Beneath it, helium burning produces carbon and oxygen. Deeper still, carbon burning produces neon and magnesium. Oxygen burning yields silicon and sulfur. And at the very core, silicon burning, occurring at temperatures of 3 billion degrees, produces iron. Iron is where the process stops. Unlike every element that precedes it, iron does not release energy when it fuses. Iron is the most tightly bound nucleus in nature, the bottom of the nuclear binding energy curve. To fuse iron requires an input of energy rather than a release, and in the core of a massive star, there is nothing left to provide that input. The iron core simply accumulates, growing denser and hotter until it reaches a critical mass of approximately 1.4 times the mass of the Sun, the Chandrasekhar limit, named for the Indian-American astrophysicist Subramanian Chandrasekhar, who derived it in 1930 at the age of 19 during a steamship voyage from India to England. When the iron core reaches that limit, it collapses. Not gradually, not over millions of years. In less than 1 second, a core the size of Earth compresses to a sphere roughly 20 kilometers across. The density it reaches is equivalent to the density of an atomic nucleus, matter so compressed that individual atoms no longer exist as distinct entities. What forms is a neutron star, an object of almost hallucinatory physical extremity, and the shock wave produced by the collapse, by the rebounding of infalling outer material against this suddenly rigid, incompressible core, propagates outward through the star at a significant fraction of the speed of light, tearing the star apart in an explosion we call a core collapse supernova. For a period ranging from days to weeks, a single supernova can outshine a galaxy of hundreds of billions of stars. The energy released in the explosion exceeds the total energy output of our Sun across its entire 10 billion year lifespan by a factor of roughly 10,000, and embedded in that energy, accelerated outward at velocities of 10,000 kilometers per second, is every heavy element the star spent its life constructing: carbon, oxygen, nitrogen, silicon, sulfur, iron, and, synthesized in the extraordinary neutron flux of the explosion itself, elements heavier than iron: gold, platinum, uranium, lead, scattered into interstellar space, seeding the next generation of molecular clouds with the chemical complexity that the Big Bang alone could never have provided. This is the mechanism. This is how a universe of hydrogen and helium becomes a universe with a periodic table. But knowing the mechanism does not fully prepare you for the scale of what it implies about your own existence. The Sun is a second-generation star, at minimum, possibly third. The heavy elements present in the solar nebula, from which it and its planets formed, the elements that make Earth a geologically and chemically complex world, were produced by at least one prior generation of stellar evolution and dispersal, possibly more. Before our Sun ignited, before the Earth condensed from a protoplanetary disk, at least one massive star had to live its entire life and die in a supernova, had to synthesize the elements in its core over millions of years, had to explode with sufficient violence to scatter those elements across light, years of space, had to wait while that material mixed with surrounding gas and slowly, over tens of millions of years, collapsed again under gravity into a new stellar system. You exist downstream of at least one stellar death, possibly several. The atoms in your body are survivors of multiple stellar generations, forged, scattered, swept up, incorporated into solid rock, dissolved by planetary chemistry, reorganized by geological processes spanning hundreds of millions of years, and eventually assembled by biology into molecules of staggering complexity. Each atom carries, in a sense, a history stretching back billions of years and billions of light years. There is no meaningful way to calculate the number of events that had to occur in the correct sequence for those atoms to be sitting inside a living organism at this particular moment in cosmic history. The astronomer Carl Sagan, who dedicated much of his life to making precisely these scales comprehensible to ordinary people, wrote in his 1980 book Cosmos that we are a way for the universe to know itself. It is a sentence that sounds like poetry, but read it again as a physical statement. The universe, for almost its entire history, was unconscious. It burned and exploded and collapsed and expanded in complete darkness, with no observer, no awareness, no experience of its own processes. And then, in one corner of one galaxy, among hundreds of billions of galaxies, the recycled wreckage of dead stars organized itself into something capable of reconstructing, with instruments and mathematics, the history of those same stars, of measuring the light from supernovae, of identifying the spectral signatures of heavy elements in stellar atmospheres, of writing the equations that describe the collapse of an iron core. The universe built, from its own debris, a mechanism for understanding itself. Whether that is remarkable or simply inevitable, whether it was always going to happen, somewhere, in some galaxy, around some star, is a question we have not yet answered. But what we can say is this: it required the deaths of an unknown number of stars. It required billions of years of patient, violent, indifferent cosmic chemistry. And it required something else, something that the deaths of stars alone could not provide. It required the right planet, in the right place, around the right star, at the right time in the right galaxy, and the probability of all those conditions converging, as we are about to discover, makes the death of a star seem like the simplest part of the story. Science has a particular relationship with the questions it cannot answer. In most fields, an unsolved problem is treated as a temporary condition, a gap in understanding that will be filled, eventually, by better instruments, more data, finer mathematics. The assumption of solvability runs so deep in the scientific tradition that it is rarely stated explicitly. It is simply there, underlying every research program, every grant application, every doctoral thesis. The universe is comprehensible. We are in the process of comprehending it. Time and effort will close the distance. And then there is abiogenesis. Abiogenesis, the emergence of living systems from non-living chemistry, is not a typical unsolved problem. It is not a gap waiting to be filled. It is, at present, something closer to an open wound in the body of scientific knowledge. A question so fundamental, so structurally resistant to resolution, and so freighted with implication that the scientific community has not yet reached consensus on the most basic terms of the investigation. Researchers disagree not only about the answer, they disagree about where to look, about which chemical systems are relevant, about what definitions of life should govern the inquiry, and, most disquietingly, about whether the event that produced life on Earth was so improbable that its repetition anywhere else in the universe is genuinely in doubt. This is not a failure of science. It is an honest account of the frontier. And the frontier, it turns out, is stranger and more vertiginous than almost anything the previous chapters have described. We need to establish what we are actually asking. Life, as it exists on Earth, is characterized by a set of properties so specific and so interdependent that defining precisely where non-life ends and life begins is itself a non-trivial philosophical problem. Living systems metabolize. They extract energy from their environment and use it to maintain order against the thermodynamic tendency toward dissolution. They reproduce. They make copies of themselves, transmitting information from one generation to the next. They evolve. The copies they make are not perfect, and the variations that arise are subject to selection by environmental pressures, producing change over time. And they are, without known exception, built from the same fundamental molecular architecture: nucleic acids storing information, proteins performing function, lipid membranes creating the bounded interior space in which chemistry can be controlled. The question of abiogenesis is the question of how that architecture assembled itself spontaneously from the inorganic chemistry of an early planet, without a template, without a blueprint, without any prior living system to catalyze the process. It is a question about a transition that happened once, in one place, between 3 and 4 billion years ago, and left no direct physical record of its occurrence. We are attempting to reconstruct, from indirect evidence and theoretical reasoning, an event that may have been unique in the history of the Earth, and possibly unique in the history of the cosmos. The difficulty of this should not be underestimated. The story of how science came to grapple with this question has a definitive beginning, and it is not where most people think. It is not Darwin, though Darwin was among the first to suggest in private correspondence, in an 1871 letter to Joseph Hooker, that life might have begun in some warm little pond, where the right chemicals concentrated and reacted under the influence of heat, light, and electricity. It is not the 19th century at all. The story begins, in its modern scientific form, on a May morning in 1953, in a basement laboratory at the University of Chicago. Stanley Miller was 23 years old and 9 months into his doctoral work under the supervision of Harold Urey when he set up an apparatus that would become one of the most famous experiments in the history of science. Urey, who had already won the Nobel Prize for the discovery of deuterium, had proposed that the early Earth's atmosphere was strongly reducing, rich in hydrogen, methane, and ammonia, poor in oxygen, and that under those conditions, the energy sources available on the young planet might drive the synthesis of organic molecules from inorganic precursors. Miller decided to test this directly. He built a closed system, 2 glass flasks connected by tubing, one containing water representing the early ocean, the other containing a mixture of hydrogen, methane, ammonia, and water vapor representing the early atmosphere. He introduced electrical sparks to simulate lightning. He heated the water. He ran the apparatus for a week. And when he analyzed the contents of the system, he found that the water had turned a striking reddish-brown color, and that the solution contained amino acids, glycine, alanine, aspartic acid, the building blocks of proteins, produced spontaneously from inorganic chemistry in less than 7 days. The paper was published in Science in May 1953, the same year, as it happens, that Watson and Crick published their description of the double helix structure of DNA. 1953 was an extraordinary year for molecular biology. Miller's result was celebrated immediately and widely, and for a time it appeared that the problem of abiogenesis was not merely solvable, but perhaps close to being solved. If amino acids could arise spontaneously from simple chemistry, perhaps the rest of the story, proteins, membranes, nucleic acids, eventually cells, would yield to similar experimental approaches. It did not. In the 7 decades since Miller's experiment, the field of prebiotic chemistry has made genuine and significant progress. It has also encountered a series of obstacles so fundamental that they have repeatedly forced researchers to reconsider the entire framework of the investigation. The amino acids were only the beginning, and the beginning, it turned out, was the easy part. Here is the problem that sits at the absolute center of abiogenesis research, the problem that has resisted every proposed solution and that drives the most heated debates at every conference in the field. It is called the chicken and egg paradox, and once you understand it clearly, it is difficult to understand how life got started at all. DNA carries the information of life. It is the archive, the blueprint, the hereditary record, passed from cell to daughter cell, across every generation of every organism that has ever lived. But DNA cannot replicate itself. It requires proteins, specifically enzymes, to copy it, to repair it, to transcribe it into the messenger RNA that carries instructions to the ribosome. DNA without proteins is biologically inert. It is a library with no readers, no building, and no door. Proteins, on the other hand, perform function. They catalyze reactions, build structures, transport molecules, receive signals, regulate processes. But proteins cannot replicate themselves. They have no hereditary capacity, no mechanism for copying their own sequence and transmitting it to a next generation. And the sequence of every protein, the specific order of amino acids that determines its three-dimensional structure and its function, is ultimately encoded in DNA. Proteins without DNA have no way to be reproduced accurately across generations. Each depends on the other for its existence. Neither can arise first. In a world without DNA, there is no template for making specific proteins. In a world without proteins, there is no machinery for replicating DNA. The two systems are locked in a mutual dependency so absolute that asking which came first feels less like a scientific question and more like a koan, the resolution that has gained the most traction in contemporary origin of life. Research is the RNA world hypothesis, and its development represents one of the more intellectually dramatic episodes in modern biology. RNA, the molecule that in contemporary cells acts as an intermediary between DNA and proteins, possesses a property that neither DNA nor proteins alone can claim. It can both store information and catalyze chemical reactions. It is, in a sense, the molecular equivalent of a Swiss Army knife, capable, in principle, of performing the functions of both the archive and the machinery. The theoretical foundations of this idea were laid across the 1960s by Carl Woese, Francis Crick, co-discoverer of DNA structure, and Leslie Orgel, each of whom independently noted RNA's dual capacity and suggested it might represent a more primitive system that preceded the DNA protein world we observe today. The term RNA world itself was coined by Walter Gilbert in a landmark 1986 paper in Nature, in which he proposed that the earliest life consisted of self-replicating RNA molecules capable of their own evolution, and that DNA and proteins emerged later as more efficient solutions to the problems RNA was already solving. The hypothesis received extraordinary experimental validation in 1989 when Thomas Seck and Sidney Altman shared the Nobel Prize in Chemistry for their independent discoveries of ribozymes, RNA molecules that can catalyze chemical reactions, including, in some cases, reactions on RNA itself. The existence of ribozymes demonstrated that the catalytic role of proteins was not irreplaceable. RNA could do chemistry. The RNA world was no longer merely plausible. It was chemically demonstrated, and yet, the RNA world hypothesis, compelling as it is, does not resolve the problem of abiogenesis. It relocates it. Because if RNA came before DNA and proteins, we now need to explain how RNA, a molecule of considerable chemical complexity, assembled itself spontaneously on the early Earth. RNA nucleotides, the units from which RNA chains are built, are not simple molecules. They require specific chemical precursors. They assemble under specific conditions. They are prone to hydrolysis, spontaneous breakdown by water, at rates that would seem to preclude their accumulation in any aqueous environment, and getting individual nucleotides to link together in the specific orientation required for a functional RNA chain, without the enzymatic assistance that living cells use to do precisely this, remains an unsolved experimental challenge. The chemist John Sutherland at the MRC Laboratory of Molecular Biology in Cambridge has made significant progress on the synthesis of RNA precursors under plausible prebiotic conditions. Work published in Nature in 2009 that demonstrated a plausible chemical pathway to pyrimidine ribonucleotides from simple starting materials. It was a genuine advance. It was also explicitly a partial solution to one component of a much larger problem. Where did all of this happen? The question of the environment in which life originated is itself fiercely contested, and the answer matters because different environments impose different chemical constraints on what is possible. Darwin's warm little pond, shallow, sunlit, subject to cycles of wetting and drying that might concentrate and polymerize organic molecules, has its proponents, including the chemist John Sutherland, and, notably, the work of researchers investigating the chemistry of lagoons and tidal pools on the early Earth. But the most extensively developed alternative is the deep-sea hydrothermal vent hypothesis, originating with the work of Günther Vectorshäuser in the late 1980s and developed most prominently by the geochemist Michael Russell, whose alkaline vent hypothesis proposes that the naturally occurring proton gradients across the mineral membranes of hydrothermal vents provided both the chemical energy and the physical scaffolding for the first metabolic systems. The discovery of hydrothermal vent ecosystems in 1977, communities of organisms thriving at the mid-ocean ridge near the Galapagos Islands, in complete darkness, powered by chemical energy rather than sunlight, demonstrated that life does not require solar energy and expanded dramatically the range of environments considered habitable. Both hypotheses have merit. Neither is proven. The honest position of origin of life research as of the current decade is that we have plausible chemical scenarios for several of the individual steps in the transition from chemistry to biology. We do not have a complete, experimentally validated pathway from inorganic molecules to a self-replicating, evolving system. The full sequence remains as yet undemonstrated. This is the point at which Francis Crick enters the story again, and this time, not as a triumphant discoverer, but as a man confronting the limits of his own field. In 1981, 28 years after he and James Watson published the structure of DNA and transformed biology permanently, Crick published a book called Life Itself. In it, he argued that the probability of life arising spontaneously on Earth through undirected chemistry was so low that it could not rationally be accepted as an explanation. His proposed alternative, called directed panspermia, was that life on Earth was deliberately seeded by an extraterrestrial civilization, perhaps billions of years ago, in the form of microorganisms sent across interstellar space. This is not a fringe position offered by someone outside the field. This is the co-discoverer of the structure of DNA, one of the founding figures of molecular biology. Concluding that the numbers simply did not add up, Crick was not endorsing religion or mysticism. He was applying probability theory to the problem and finding the result intolerable. The probability of the spontaneous assembly of even a single functional protein from random amino acid sequences, given the number of possible sequences and the specificity required for function, is a number so vanishingly small that, as the astronomer Fred Hoyle and the mathematician Chandra Wickramasinghe calculated in their 1981 book Evolution from Space, it resembles the probability of a tornado assembling a functioning Boeing 747 from the contents of a scrapyard. Hoyle's tornado metaphor became one of the most quoted and contested analogies in all of science. The scientific response to these probability arguments has been, broadly, to note that they misrepresent the process, that evolution and natural selection work precisely by accumulating small, individually probable steps, rather than assembling complex systems in a single event, and that the same logic applies to prebiotic chemistry. The probability of any specific pathway is not the same as the probability of any pathway. This rebuttal is legitimate. It is also, by itself, insufficient, because we have not yet identified the pathway. We know that one must exist because we are here. We do not yet know what it was. What the origin of life has taught science, after 70 years of dedicated investigation, is something more unsettling than any specific answer could have been. It has taught us that the transition from chemistry to biology is genuinely, fundamentally different in character from any transition that preceded it. The formation of atoms, the ignition of stars, the synthesis of heavy elements, the condensation of planets, all of these are processes we understand mechanistically, mathematically, with quantifiable probabilities and confirmed predictions. Abiogenesis is not yet in that category. We know it happened. The evidence in the fossil record, in the ancient carbon isotope signatures of early sedimentary rocks, in the universal genetic code shared by every living thing on Earth, places the origin of life at somewhere between 3.5 and 4 billion years ago. Perhaps earlier. We know it was a transition of staggering consequence, and we know that on the other side of it, something existed that had never existed before in the history of the cosmos, a system capable of preserving its own complexity, replicating it, varying it, and passing it forward through time. What we do not know, and what the field has not yet given us, is how. And that uncertainty does not diminish science. It is science in its most honest and most courageous form, staring directly at the most important question it has ever faced, without flinching, without fabricating certainty it does not possess, and without pretending that the frontier is anywhere near as close as we once believed. But here is the thing about frontiers. The closer you get to them, the more the landscape changes. Because the question of how life began on Earth cannot be separated, for much longer, from a question that reframes everything we have discussed so far. A question about where, in this vast and ancient universe, the conditions for life have been met before, and what the answer to that question, in its silence, is beginning to tell us. There is a moment in the development of every scientific field when the assumptions baked into its foundations are suddenly, uncomfortably visible. When what had been treated as background, as so obvious it required no examination, steps forward and demands to be questioned. For the search for extraterrestrial life, that moment arrived gradually through the accumulation of evidence that nobody initially wanted to take at face value because its implications were too stark and too lonely to sit with comfortably. The assumption was this: that Earth is ordinary, that a planet capable of producing complex life is not exceptional, that the universe, given its age and its scale, is almost certainly populated with worlds as chemically rich, as geologically active, and as biologically productive as our own. This assumption has a name in the philosophy of science: the principle of mediocrity, and for most of the 20th century, it was not merely accepted, it was celebrated, held up as the mature, anti-anthropocentric position, the Copernican correction, applied not just to our place in the solar system, but to our planet's place among the billions. It is a reasonable assumption. It feels correct. It fits our intuitions about a universe so vast that surely, somewhere, among hundreds of billions of galaxies, each containing hundreds of billions of stars, the conditions that produced us have been replicated countless times, and it may be profoundly, disquietingly wrong to understand why we need to spend time with a number, not an abstract cosmological number of the kind we encountered in the first chapters, not 10 to the power of 120, not quantities beyond any human intuition. This number is accessible, comprehensible, and somehow, because of that, more disturbing. In 2020, the astronomers Andrew Westphal and David Kipping, working with updated stellar and exoplanet data from the Kepler Space Telescope mission, estimated that there are approximately 300 million potentially habitable planets in the Milky Way alone, worlds orbiting within the habitable zones of sun-like stars at distances where liquid water could plausibly exist on a planetary surface. 300 million in one galaxy, and there are somewhere between 2 trillion and 2 trillion galaxies in the observable universe, according to a 2016 study by Christopher Consellis and colleagues published in the Astrophysical Journal. On those numbers, the universe should be overflowing with life, teeming with it. Not merely microbial life, but, given the ages of many stellar systems that predate our own by billions of years, civilizations that have had time to spread across their galaxies, to build technologies of unimaginable sophistication, to make their presence known across interstellar distances in ways that any sufficiently sensitive instrument should be able to detect. And yet, silence. Enrico Fermi asked his famous question in the summer of 1950 at Los Alamos, New Mexico. He had been having lunch with colleagues, the physicists Edward Teller, Emil Konopinski, and Herbert York, and the conversation had drifted, as conversations among nuclear physicists sometimes do, toward the question of extraterrestrial intelligence. Fermi had been reading a New Yorker cartoon that morning, a satirical piece about alien visitors. The conversation turned to the statistical likelihood of intelligent life elsewhere in the universe. And then, apparently without particular ceremony, Fermi asked, "Where is everybody?" The question sounds simple. It is not. What Fermi was identifying, and what the physicist and author Michael Hart formalized in a 1975 paper that gave the paradox its rigorous expression, is a genuine, logical contradiction between the apparent probability of extraterrestrial civilizations and the complete absence of any evidence for them. If the probability of life is high, if civilizations tend to develop technology, if technology eventually produces the capacity for interstellar communication or travel, then the galaxy should long since have been explored, colonized, or at the very least filled with signals detectable by radio telescopes. None of these things are observed. Not one, not a signal, not an artifact, not an anomaly that has resisted every non-biological explanation. The SETI program, the search for extraterrestrial intelligence, has been listening since Frank Drake pointed the Green Bank radio telescope in West Virginia at the star Tau Ceti on the 8th of April, 1960, in the first systematic search for artificial radio signals from another civilization, a project he called OSMA. In the 6 decades since, the search has expanded to encompass thousands of stellar targets, multiple frequencies, and, in the Breakthrough Listen initiative, funded by Yuri Milner and launched in 2015, the most comprehensive and well-resourced search in the program's history. Breakthrough Listen has examined over 1 million stellar sources and has produced, to date, no confirmed detection of an artificial signal of extraterrestrial origin. The silence is not absence of data. It is an overwhelming abundance of negative data, and negative data, at sufficient scale, begins to carry its own message. There are many proposed resolutions to the Fermi paradox, and they range across a spectrum from hopeful to genuinely horrifying. Perhaps civilizations are common, but interstellar travel is so difficult that they never spread beyond their home systems. Perhaps they communicate on frequencies or through methods we have not yet thought to look for. Perhaps they have chosen silence, a kind of cosmic caution motivated by the awareness that announcing your presence to a universe of unknown inhabitants might not be wise. This last resolution was articulated most disturbingly by the Chinese science fiction author Liu Cixin in his 2008 novel, The Three-Body Problem, as the Dark Forest Hypothesis. The idea that the universe is silent because every civilization that survives long enough understands that silence is survival. These resolutions are possible. Some are more credible than others. But there is a different category of resolution, one that does not depend on the behavior of civilizations at all, but on the conditions required for their existence. One that proposes the silence is not behavioral, but structural, that the universe is silent not because civilizations are hiding or communicating in ways we cannot detect, but because civilizations, complex, multicellular, technologically capable life, are extraordinarily rare, perhaps vanishingly rare, perhaps outside of Earth, non-existent. This is the rare Earth hypothesis, and it is, in the context of everything we have covered in this series, the argument that completes the picture most coherently. The formal articulation of the rare Earth hypothesis was published in 2000 by the paleontologist Peter Ward and the astronomer Joe Kirschvink. Though the argument draws heavily on Kirschvink's prior work on the snowball Earth hypothesis and on Ward's decades of research into mass extinctions and the fragility of complex life across geological time, their book, Rare Earth: Why Complex Life is Uncommon in the Universe, assembled a case that the conditions required for the emergence of complex multicellular life are not merely a planet in the habitable zone, but an extraordinary convergence of geological, astronomical, and geophysical factors, each one individually improbable, collectively representing a configuration that may occur only once or a handful of times in the entire observable universe. Let us work through the factors, because the cumulative weight of them is what matters. Begin with location, not just the location of the planet within its solar system, but the location of the solar system within its galaxy. The Milky Way, like all spiral galaxies, has a structure, a dense, violent central region dominated by intense radiation, frequent supernovae, and the gravitational influence of a supermassive black hole. Outer spiral arms that are metal poor, too chemically impoverished to form Earth-like rocky worlds, and an intermediate region, the galactic habitable zone, first defined by the astrobiologist Guillermo Gonzalez in a 2001 paper in Icarus, where the balance between heavy, element abundance and environmental stability is most favorable. Our solar system sits in this zone, at approximately 26,000 light-years from the galactic center. Too much closer and sterilizing radiation events would likely have interrupted the development of complex life. Too much further, and the planet-forming chemistry would have been insufficient. This is one filter, one condition. The list continues. Our star, the Sun, is not merely a star. It is a G-type main sequence star of unusually stable luminosity, not given to the violent flaring events that characterize the more common M-dwarf stars, which are estimated to account for approximately 75% of all stars in the galaxy. M-dwarf stars are interesting astrobiologically because their habitable zones are close in, meaning habitable planets are tidally locked, permanently facing the star on one side, permanently dark on the other, and because their early lives are characterized by intense ultraviolet and X-ray flaring that may strip planetary atmospheres before life has a chance to establish itself. The evidence from the TRAPPIST-1 system, 7 roughly Earth-sized planets orbiting an M-dwarf 40 light-years from Earth, suggests that atmospheric retention around such stars is a genuine challenge. Our Sun, by contrast, has maintained a luminosity stable to within a few percent across 4.5 billion years, long enough for evolution to do its extraordinarily slow and patient work. Our Moon is not merely a moon. It is a moon of anomalous size, roughly 1/4 the diameter of Earth, a ratio that has no parallel among the rocky planets of the inner solar system. The leading model for the Moon's formation, the giant impact hypothesis, first developed by William Hartmann and Donald Davis in 1975, proposes that approximately 4.5 billion years ago, a Mars-sized protoplanet called Theia struck the proto-Earth in a glancing collision, ejecting material that eventually coalesced into the Moon. The consequences of this collision for the development of life are difficult to overstate. The Moon's gravitational influence stabilizes Earth's axial tilt within a range of approximately 22 to 24.5 degrees over timescales of tens of thousands of years. Without this stabilization, as the mathematician Jacques Lascar and his colleagues demonstrated in a 1993 paper in Nature, Earth's axial tilt would vary chaotically between near zero and approximately 85 degrees, producing climate oscillations so extreme that the development of complex life might have been impossible. Mars, which lacks a large stabilizing moon, is believed to have experienced precisely this kind of axial chaos across its history. Jupiter, the largest planet in our solar system, with a mass more than twice that of all other planets combined, acts as a gravitational shield. Its enormous mass intercepts comets and asteroids on trajectories that would otherwise threaten the inner solar system, deflecting them into less hazardous orbits or capturing them entirely. The astrophysicist George Wetherill estimated in a 1994 paper that without Jupiter, the frequency of large impactor strikes on Earth would be approximately 10,000 times higher than it is. A bombardment rate under which the development of complex life might be chronically interrupted. The Chicxulub impactor that triggered the mass extinction 66 million years ago, the event that ended the non-avian dinosaurs and opened the ecological space into which mammals and eventually primates expanded, was, by geological standards, a relatively modest event. At 10,000 times the impact frequency, events of that magnitude would recur on timescales far too short for complex ecosystems to recover between them. Plate tectonics, the slow movement of the crustal plates that cover Earth's surface, driven by convective currents in the mantle, is not a universal planetary feature. Mars, Venus, and the Moon do not have active plate tectonics in any recognized form, and yet plate tectonics is, according to the geobiological evidence, central to the long-term habitability of Earth. It drives the carbon silicate cycle, a geochemical thermostat that has maintained Earth's surface temperature within the range of liquid water across 4.5 billion years, despite the fact that the Sun was approximately 30% dimmer in the Archean era than it is today. Without plate tectonics, without the subduction of carbonate-bearing ocean crust and the subsequent outgassing of CO2 from volcanoes, the long-term regulation of Earth's climate is difficult to maintain. That regulation has been the background condition for the entire history of life on this planet, and Earth's magnetic field, generated by the convective flow of molten iron in the outer core, deflects the charged particles of the solar wind that would otherwise strip away the atmosphere and subject the surface to lethal levels of ionizing radiation. Mars lost its magnetic field somewhere between 4.2 and 3.9 billion years ago, and with it, over geological time, most of its atmosphere. The thin Martian atmosphere today, less than 1% of Earth's surface pressure, is the consequence. Stack these filters: galaxy location, stellar type, and stability. A large moon from a specific impact, a gas giant shield, active plate tectonics, a planetary magnetic field, each one individually improbable, each one individually necessary. Together, they define a configuration so specific that the probability of replication elsewhere depends critically on whether each factor is truly required, and on the extraordinary coincidence that, on one particular planet, orbiting one particular star, in one particular region of one particular galaxy, all of them converged simultaneously. Ward and Kirschvink were not claiming that simple microbial life is rare. Microbial life may well be widespread. There are credible hypotheses for its existence in the subsurface oceans of Europa or Enceladus, in the clouds of Venus, perhaps in the ancient hydrosphere of Mars. The rare Earth hypothesis is specifically a claim about complex life, about multicellular organisms, about ecosystems of sufficient stability to sustain the 3 billion year experiment that produced eyes, nervous systems, cognition, and technology. That specific outcome, they argued, required not just chemistry and water. It required an almost geological conspiracy of favorable conditions persisting across timescales so vast that the word stability barely captures the requirement. The silence of the sky, in this reading, is not a mystery to be solved. It is an answer to the question of how common our kind of complexity is. And the answer is, perhaps not common at all. Perhaps the universe has been running this experiment for 13.8 billion years, on trillions of planets, in billions of galaxies, and the result, so far as we can determine from the evidence available to us, has been produced exactly once, here, in this solar system, on this planet, in this biosphere. And if that is true, if the rare Earth hypothesis is even approximately correct, then the question is no longer simply how life got started. The question becomes something far more disorienting, something that reaches back through everything we have covered in the previous 4 chapters and recontextualizes all of it. If the universe accidentally created life on Earth, and if Earth may be the only place it succeeded, then what exactly is the universe doing? What is the point, if there is one, of a cosmos that spent 13.8 billion years building the conditions for a single experiment? And what happens to our understanding of reality when we consider that the experiment may not be finished, and that the answer it is moving toward may be something science has not yet developed the language to describe? Every story told about the universe eventually arrives at a wall, not a wall of ignorance in the ordinary sense, not a gap that more data or better instruments might eventually close, but a wall of a different and more fundamental character, a point at which the questions the universe generates about itself exceed the capacity of the universe's own inhabitants to answer them, a point at which science, philosophy, mathematics, and the unaided human mind all arrive simultaneously at the same threshold and find that nothing beyond it is directly reachable. We have been building toward that wall across 5 chapters. We have traced the universe from its first fraction of a second, through the asymmetry that saved matter from annihilation, through the stellar deaths that built the periodic table, through the improbable chemistry that produced life, and through the extraordinary convergence of planetary conditions that may have made Earth unique in the observable cosmos. Each chapter has been, in a sense, a step closer to the wall, and now we are standing in front of it. What is on the other side is not darkness. It is something stranger. It is a set of ideas so large, so structurally destabilizing, and so resistant to ordinary intuition that physicists who work with them daily report a persistent, low-grade vertigo, the feeling of standing on an intellectual surface that does not quite hold your weight. These ideas do not make the universe smaller or simpler. They make it so large and so strange that the word universe, the word we have been using to mean everything that exists, may turn out to be a radical underestimate of the territory. We need to begin with inflation, not in the economic sense, but in the cosmological one. The theory that in the first 10 to the power of negative 36 seconds after the Big Bang, the universe underwent a period of exponential expansion so violent that a region smaller than a proton expanded to roughly the size of a grapefruit in an interval of time so short it defies any analogy. This expansion was not the familiar expansion of space described by Edwin Hubble in 1929, the gradual recession of galaxies from one another that we observe today. It was expansion at a rate that, during its brief duration, was faster than light. The inflationary hypothesis was proposed in 1980 by the physicist Alan Guth, then at Stanford, as a solution to 3 specific problems in standard Big Bang cosmology: the horizon problem, the flatness problem, and the magnetic monopole problem. that the original theory could not resolve. What Guth found, to his own considerable surprise, was that a period of exponential expansion in the earliest moments of the universe solved all three problems simultaneously. The paper, published in Physical Review D in 1981, is one of the most cited in the history of cosmology. Its central prediction, that the universe should be geometrically flat on the largest observable scales, has been confirmed to extraordinary precision by measurements of the cosmic microwave background radiation. But inflation brought with it a consequence that Guth and his colleague, Paul Steinhardt, and later Andre Linde, did not initially anticipate, or, when they did, were not entirely comfortable with. Once inflationary expansion begins, it does not stop everywhere simultaneously. Quantum fluctuations in the inflationary field cause some regions to stop inflating, while others continue. Those continuing regions themselves develop fluctuations, producing further pockets of stopped inflation. The process is, in the mathematics, self-reproducing, eternal. It generates not a single universe, but an effectively infinite ensemble of them, each pocket of stopped inflation constituting a separate universe with its own physical properties, its own constants, its own initial conditions. Inflation, if it occurred at all, almost certainly generated a multiverse. Andre Linde, who developed the theory of chaotic inflation throughout the 1980s at the Lebedev Physical Institute in Moscow and later at Stanford, described the implication with characteristic directness. The universe we observe is not the universe. It is one universe, one inflated pocket among an uncountable infinity of others, each as real as ours, most utterly different from it, nearly all of them uninhabitable. String theory arrives at the same destination from a different direction. The theoretical framework that physicists have spent 4 decades attempting to develop as a unified description of quantum mechanics and general relativity, the two pillars of modern physics that are, in their current forms, mathematically incompatible, predicts not one set of physical laws, but something in the vicinity of 10 to the power of 500 distinct sets of them. Each set corresponds to a different configuration of the extra spatial dimensions that string theory requires, compactified at scales too small to detect. Each configuration produces a different universe with different physical constants, different particle masses, different forces, different chemistry, different possibilities. 10 to the power of 500 is a number that makes the cosmological constant's fine-tuning ratio look modest. It is, for most practical purposes, indistinguishable from infinity. And if the string theory landscape, as Leonard Susskind named it in his 2003 paper, The Anthropic Landscape of String Theory, is real, then every one of those configurations is potentially realized somewhere in the eternal inflationary multiverse. Every possible universe exists, somewhere, in some pocket of the eternally inflating space. There is a universe where the fine structure constant is twice what it is here, where carbon cannot form, where stars burn for a millisecond and collapse. There is a universe where the cosmological constant is 1,000 times larger, where galaxies never assembled, where the whole cosmos expanded and thinned before a single atom could fall toward another under gravity. There are universes of extraordinary complexity we cannot imagine, governed by physics we have no framework to describe, and in the vast, cold, dark majority of them, nothing, no chemistry, no stars, no time worth inhabiting. The physicist and Nobel laureate Steven Weinberg was among the first to recognize the profound and uncomfortable implication of this for the fine-tuning problem. In a 1987 paper, years before the accelerating expansion of the universe was confirmed observationally, Weinberg used the anthropic principle and early multiverse reasoning to predict that the cosmological constant, if it existed and was not exactly zero, should be small enough to permit galaxy formation, but not so small as to suggest supernatural precision. When the accelerating expansion was discovered in 1998 by the teams led by Saul Perlmutter, Brian Schmidt, and Adam Rees, work that earned them the Nobel Prize in Physics in 2011, and the cosmological constant was measured. Its value sat precisely in the range Weinberg had predicted. The anthropic argument had produced a genuine scientific prediction, and the prediction was correct. This is not a trivial result. It means that the logic of the multiverse, the reasoning that observers can only exist in configurations compatible with observers, has predictive power. It is not merely a philosophical position. It has, in at least one case, anticipated an observational result before the observation was made. That gives it a claim on scientific seriousness that its detractors have found genuinely difficult to dismiss. But here is the thing that Weinberg himself confronted in his 1977 book, The First 3 Minutes, in a sentence that has shadowed physics ever since. The more the universe seems comprehensible, the more it also seems pointless. He wrote those words before the multiverse entered mainstream cosmological discourse. He was expressing the existential weight of a universe with no discernible center, no hierarchy of importance, no indication that any location or configuration within it was privileged. In the multiverse, that weight becomes almost unbearable. If our universe is one of an infinite number, if its fine-tuned constants are not remarkable because remarkable configurations are inevitable in an infinite ensemble, then the universe that produced you carries no special status. It is a statistical inevitability. It could not have failed to exist somewhere because everything exists somewhere. The improbability of our cosmos is not resolved. It is absorbed into an infinity so large that improbability loses its meaning. And yet you are here, and the universe in you is aware of itself. There is a perspective that sits at the intersection of physics and philosophy, articulated most carefully by the physicist John Archibald Wheeler, the man who coined the terms black hole and quantum foam, who supervised the doctoral work of Richard Feynman, who spent a career at the edge of what physics could say about the nature of reality. Wheeler spent the last decades of his life developing what he called the participatory universe, the idea, drawn from the implications of quantum mechanics, that the act of observation is not merely passive registration, but active participation in the determination of physical reality. In quantum mechanics, a system does not possess definite properties, position, momentum, spin, until it is measured. The measurement is not revealing a pre-existing value. It is, in some sense, establishing it. The Copenhagen interpretation of quantum mechanics, which remains the most widely used framework among working physicists, holds that the wave function of a particle, the mathematical object encoding the probabilities of all possible measurement outcomes, collapses to a definite value only when an observation occurs. Wheeler pressed this idea to its cosmological limit. If observation participates in determining physical reality, and if observers are themselves products of the universe, then the universe, through its observers, participates in its own determination. It is, in some sense, self-referential, self-creating, not in a mystical sense, but in the rigorous sense that the mathematics of quantum mechanics allows. Wheeler summarized this intuition in a diagram he drew repeatedly in his later years, a large U-shaped figure with an eye at one end looking back at the other end. The universe, he was suggesting, brings observers into existence through its evolution, and those observers, by their existence, by their measurements, by their capacity to retroactively fix the properties of quantum systems across time, complete the circuit. The universe, through conscious observers, participates in its own creation. This is not a proven theory. It is not even a theory in the strict scientific sense. It is a framework for thinking about what quantum mechanics implies at cosmological scales, and physicists disagree about its interpretation as sharply as they disagree about almost anything in fundamental physics. But it represents the most serious attempt in the history of science to ask what the existence of observers means for the universe that produced them, and it arrives at an answer that is neither comfortable nor dismissible. It means something. Observers are not accidental passengers in an indifferent cosmos. They are, in Wheeler's framework, the mechanism by which the cosmos becomes real. Let us stand back from the specific theories and hold the entire arc of this series in view. We began with a question that sounded simple. How did the universe accidentally create life on Earth? And across 5 chapters, we have watched that question expand. We have discovered that the accident required the precise calibration of at least half a dozen fundamental constants to tolerances that make 1 in a trillion look generous. It required a 1 in a billion asymmetry between matter and antimatter that should not exist, but does. It required the deaths of stars that lived and exploded before our solar system existed. It required a chemistry so complex and so poorly understood that the co-discoverer of DNA concluded it was essentially impossible by chance alone. It required a planet configured by an improbable collision with a Mars-sized body, shielded by a fortuitously placed gas giant, stabilized by an anomalously large moon, regulated by a geological mechanism that most rocky planets do not possess. And then, in this final chapter, we have discovered that the framework capable of explaining the fine-tuning of the constants leads inevitably to the existence of infinite other universes, that the universe we inhabit may be one of an uncountable ensemble, most of which are dark and empty and structureless, that the logic used to predict the value of the cosmological constant from first principles invokes the existence of observers as a necessary component of the argument, that the most serious attempt to understand what observers mean at a cosmological level suggests the universe is, in a precise and non-metaphorical sense, completing itself through the existence of minds capable of registering it. What are we to do with this? There is no clean answer. There is no final resolution that ties the threads into a comprehensible conclusion. And that, it turns out, is not a failure of the inquiry. It is the most honest thing the inquiry can offer. The philosopher Thomas Nagel, in his 2012 book Mind and Cosmos, argued that the emergence of consciousness through the blind, undirected processes of physics and evolution is so improbable as to strain the materialist framework within which science operates. He was not arguing for intelligent design. He was arguing that our current theories may be fundamentally incomplete, that they lack the resources to account for the fact that the universe produced minds at all, and that any complete account of reality will need to take that fact seriously as a structural feature of the cosmos, not a contingent accident within it. The book was ferociously attacked by some philosophers and quietly agreed with by others. Its central discomfort has not been resolved. The physicist Lee Smolin, in his theory of cosmological natural selection, proposed that universes reproduce through black holes, with the constants of each daughter universe slightly modified from the parent, a mechanism that, over cosmological timescales, would select for universes that maximize black hole production. Smolin's theory is testable in principle, and it makes the existence of fine-tuned constants a product of selection rather than chance or design. It is a genuinely original and scientifically serious idea. It is also, at present, unconfirmed. The physicist Max Tegmark, in his mathematical universe hypothesis, proposed that every mathematically consistent structure exists as a physical reality. That existence is not something added to mathematical description, but identical with it. In Tegmark's framework, the question of why the universe exists at all dissolves. Every possible universe exists, by definition, because existence is what mathematical structures do. Whether this is a profound insight or a category error disguised as cosmology is a debate that physics and philosophy have not yet settled. These are the positions at the frontier. Not one of them is the answer. All of them are serious attempts by serious minds to stand at the edge of what is knowable and reach, with whatever tools are available, toward what is not. Here is what we know. The universe is 13.8 billion years old. It began in a state of almost perfect symmetry and near-perfect uniformity. It is governed by a set of constants whose values sit inside ranges so narrow that deviation in any direction would have produced a cosmos of total sterility. From a 1 in a billion imbalance between matter and antimatter, it produced atoms. From gravity acting on hydrogen and helium over hundreds of millions of years, it produced stars. From the deaths of those stars, it produced the chemical complexity that made biology possible. From a planet assembled in a solar system configured by a series of individually improbable events, it produced, after 4 billion years of relentless chemical and biological experimentation, a species capable of reconstructing the entire history of the process that produced it. That species is now asking, with the full force of its most powerful instruments and its most rigorous reasoning, whether it is alone. And the answer, tentatively, provisionally, and with all the appropriate scientific caution that the question demands, appears to be possibly yes. If that is true, if the universe ran this experiment for 13.8 billion years across 2 trillion galaxies and produced minds in only one place, then we are not an accident in the ordinary sense. An accident, properly understood, is an event without significance. What we are may be something closer to an inevitability that only just barely happened. A solution to a problem so constrained, so demanding of specific conditions, that the margin between a universe with minds and a universe without them is measured in the tolerances of physics at the Planck scale. The universe did not intend to create life on Earth. It had no intention. It had no awareness that it was doing anything at all. For most of its history, it was simply a vast, cold, violent, indifferent process, burning and collapsing and expanding in complete darkness, with no one to observe it and no need for an observer. And then, in one corner, in one unremarkable spiral galaxy, around one middle-aged star, on one small rocky planet, something happened. The chemistry crossed a threshold. Evolution explored its space. Cognition emerged. And for the first time in 13.8 billion years, the universe was no longer alone with itself. Whether that matters, whether mattering is even a category the universe possesses, is the question that physics cannot answer. Philosophy has tried. Religion has tried. Poetry has tried, perhaps more honestly than either. None of them has closed it. What we are left with, at the end of this story, is not resolution. It is something more durable than resolution. It is the full, unobstructed weight of the question itself. The question that the universe, through you, is asking about its own existence. The question that has no answer yet. The question that may be the most important thing we do, not because we will solve it, but because the asking of it is what it looks like when matter becomes aware that it exists. The universe did not create you on purpose, but it created something that would spend its entire existence wondering why. And in a cosmos this large, this old, and this strange, that may be the most remarkable thing that has ever happened.